Welcome to NASA Edge, an inside and outside look at all things NASA. Wow, what an historic launch. Now, this is going to be the first time we're going to be seeing a spacecraft that's going to be launched from the West Coast. And joining us now is the newest NASA Chief Scientist, Jim Green. How you doing, sir?
Hey, Chris. Good to be here.
Now, I know it's going to be kind of hard, but in about a minute, could you kind of share with the audience what we know about Mars up to this point before InSight?
All right. Well, you know, we've got orbiters, we've got landers, and we've got rovers. And for the last couple decades, they've been scouring the system and really getting a great idea to what that planet's all about. On the surface, we're finding plenty of evidence for past water, and I mean a significant amount of it. 2/3 of the northern hemisphere was perhaps underwater, perhaps is a mile deep. Now, in addition to that, we also see that the solar wind is stripping the atmosphere. Part of that, we believe, is probably due to the fact that Mars lost its magnetic field in its past. And this is where InSight comes in, because what we want to do is we want to be able to land InSight, be able to deploy instruments and get inside and really understand the interior of the planet.
Yeah, that's a good point. We want to look at the vital signs. I mean, there's some really cool things. Now, when you look at the InSight mission, what's probably the one thing that you're hoping to get away from InSight?
Well, there'll be plenty of surprises. We believe Mars is quaking. There's plenty of evidence that seem to indicate that that body shakes. But we want to know how often. We want to know how strong. I mean, not only from a fundamental planetary science perspective of understanding the size of the core, whether it's part of its liquid or not, the size of the mantle and the crust, so that we can compare it against the Earth. But we also want to know, when humans go there, how they're going to build habitats to withstand an environment that may have occasional Marsquakes.
Now, I tell you what, now with this particular mission, you have something on you.
Yes.
That's pretty popular with the public. What do you have?
Well, we know Mars is pretty popular indeed with the public, and so we had an opportunity for everyone to send in their name, and we put their name on a chip. And if I can open this bag, I can get the chip out. I should have probably had it out sooner.
That's okay. It makes the excitement's brewing, you know?
It has 2.4 million names on this chip.
That's pretty impressive. I tell you what, I think my son's name is on that chip too.
My name's on that chip.
Well, I tell you what, Jim, you know, we're going to be learning all about InSight and MarCO. And Blair, Franklin, and I had a chance to travel to Jet Propulsion Laboratory to learn about InSight. Let's check it out. We're here with Tom Hoffman, Project Manager for InSight. How you doing, Tom?
I'm doing great, Chris.
You getting pretty excited?
I'm very excited. We're getting really close. I can't wait to go.
Hey, tell us, what is InSight?
InSight is a geophysical lander that's going to go to Mars. It's going to land on Mars. It's going to deploy some geophysical instruments, specifically a seismometer and a heat flow and physical properties probe, and it's going to probe into the interior of Mars to understand what the makeup is. You can think of it kind of as a checkup for Mars.
This is a pretty cool mission because it's not like any other Mars mission that we've had to the surface before.
That's right. So in the past, we've only gone a few centimeters into the surface of Mars, just basically scrape the surface. In this mission, we're going to literally hammer in 5 meters, about 15 feet, into the regolith of Mars, so that we can put down a physical properties probe. What it's going to do, as it goes in, it's going to take measurements of the properties of the regolith, which is the soil, at different intervals. And finally, when it gets down to its final resting spot, about that 5 meters, 15 feet down, it's going to be able to measure how much heat is coming out from the core to the surface. And the reason that matters is because with a hot core, we know that that's what basically keeps the whole planet alive, that hot core. So understanding how hot it still is and how much energy is still coming out from the core will really give us a good idea about how alive is Mars still today.
Bruce, it's absolutely fascinating to think of Mars as a living planet, but how do you do that scientifically?
Well, a planet is really, it's like a heat engine. You have the heat of the core that's trying to get out, and that's what's driving all the geology on the planet. And so what we need to measure are both the heat coming out, which is its energy balance, and sort of the motions that are going on. And we measure those with our 3 investigations.
How does that help you determine that information about the composition of the planet that you guys are looking at?
Well, the different parts of the planet have different masses. So the iron core is very dense and very heavy. And so what we'd like to know is how big that core is. And the size of the core is going to determine its effect on the wobble of the planet. So we can measure the size of the wobble, the speed of the wobble, and also the frequency, because it wobbles at different frequencies. And so all those things we can then sort of trace back to the size and the density and state of the core.
Do we have any indication so far that there's either a lot of seismic activity or rather enough seismic activity to get the data that you're looking for?
Well, we have some information. We have images from orbit that show us faults on the surface of the planet, and most of those faults are billions of years old, but we actually can see some that are younger, and by counting up the faults as a function of time, extrapolating it to the present, we can come up with an estimate of the Mars activity. We also have sort of bounding cases. We know that the Earth is going to be a lot more active than Mars. We know that the Moon is a much deader planet. We measured seismic activity on the Moon during the Apollo age, so we know that Mars should be more active than that, and the numbers that we estimate do come out between those two bounds, and so we have a good expectation that we'll see Mars quakes, but of course we won't really know until we get there.
So Dr. Ashite, InSight has landed. Everybody's looking forward to start collecting science, but before you can start collecting science, you have to start deploying your instruments. Tell me a little bit about that.
So the first thing we'll do is we document our workspace using our camera on our arm. We'll take about roughly 56 images that have to be downlinked. It could take a few sols, a couple of sols to downlink them. Once those images arrive, they're downlinked, they'll be processed on the ground to build a digital elevation map of our workspace. The scientists and engineers are now going to work together very closely to select the two places they want to place the instruments. So once those sites have been selected, then we go on our merry ways to build sequences to actually pick these instruments and put them on the surface of Mars. The first one is the seismometer, and then once you're done placing the seismometer on the ground, this seismometer is very, very sensitive. If a butterfly sits on top of it and flaps its wings, it can detect it. So you can imagine if you have wind or any other disturbance going over the seismometer, you're going to get noise on your signal. So we have to put over it what we call a wind and thermal shield. Basically, it provides the seismometer a constant thermal environment and also protects it from the wind.
Now, when you put your heat probe down, once that starts drilling into the surface of Mars, that is, you're done with that, right? That cannot be moved.
Yes, that is correct. So what we do with the heat probe is we go through the same process. We work with the scientists, we select a site. Once we're done with that, we take our robotic arm, which is basically a fishing pole with a hook on it. You pick up the heat probe. It's got what we call a tether or a cable, because it's all mated to the lander. It gets its power and data and computing power from the lander. We pick it up, and as we move it, the tether is inside the heat probe, and we pull it out, and then we slowly bring it to the ground. It's very light, and we have to also be precise to place it at a position where there will not be any obstacles that would block what we call the mole from getting to the ground, from digging into the ground.
The seismometer is on the surface of Mars. The heat probe has dug down into the surface. What if you find out that the center of Mars is solid, that it isn't molten, it isn't hot? What does that tell you?
It tells us we've got some good science, right? Because whether it's molten, whether it's solid or liquid, it's the right answer. So that means we have the right answer, we have the better model for Mars. So it's a win-win.
Joining us now is Sue Smrekar, who is the Deputy Principal Investigator for InSight. Now, Sue, one of the questions that I have, I'm super interested in the whole seismic component to this mission, because I got to be honest, I never really thought of Mars quakes before, but I'm wondering, what is the current sort of seismic activity on Mars? What do we know, and what do we expect to know?
Yeah, well, there's actually several ways that we have estimated the number of quakes. Probably the most straightforward one is from small impacts. You know, the atmosphere of Mars is 1/100th the density of Earth, so very small things that, you know, would burn up in Earth's atmosphere actually hit the ground and create impact craters that generate seismic waves. And because we have such, you know, great resolution from our orbiters, we've actually been able to count the number of impacts hitting the surface above a certain size over the last 10 or 20 years. And in fact, what we see are these dark streaks where the dust is blown away off the surface. So that brings us in to look at the smaller craters. We see them in the low resolution, then we go to the high resolution. So that's quite a firm number.
The interesting thing about InSight is we're actually, for the first time, going to dig under the surface. What are you going to get from digging down and getting all that data, and what's it going to tell us about the seismic activity?
So I'm super excited to get this heat flow data. I've been working for the last 20 years to get this data.
Well, no wonder you're so nervous about 5 hours from launch. I would be nervous too.
Yeah, it's a thrill for sure. So we will get a measure of the heat coming out of the planet. And that is a real indication of the energy that a planet has to drive geologic activity. You know, every planet is an engine, and that drives all of the geologic activity, which contributes to what's going on in the atmosphere. So it's really the fundamental measurement of how active and how much faulting we expect on a planet.
Yeah. Well, it's interesting because Franklin actually was saying, well, what if we find that, nothing's going on down there? That's still kind of a scientific result, right?
Yeah, well, so there's actually two contributions to heat flow. There's cooling of the planet, and every planet cools. There's no getting around that. So there's going to be some heat coming out. And the other contribution is from radiogenic elements, uranium, thorium, potassium, that decay over time. So those elements, as they decay to other isotopes, to other elements, it generates heat. And we know that there are some radiogenic elements, and we think the concentration is similar to the Earth. That's actually a big question that we want to answer. Is the concentration like the Earth? And so, we have every reason to think that we will get heat coming out of the interior. It's almost impossible to have nothing.
Right.
So the question is how much?
Yeah. Well, that's awesome. We're very excited about InSight. Thanks for being on the show. InSight isn't the only spacecraft traveling to Mars. It will be joined by the MarCO CubeSats. Franklin had a chance to sit down with Annie Marinan, systems engineer, to talk about the technologies being developed on MarCO.
So Annie, there are 3 new technologies that are going to be demonstrated on MarCO. Tell me what they are.
So the 3 technologies that MarCO will be demonstrating are a propellant system that uses a fire extinguisher fluid to navigate MarCO around. There is a radio that is about the size of a softball that was designed at JPL to interface with the Deep Space Network. And there is an antenna. It's a deployable antenna that's completely flat and it can fold up. But when it operates, it actually simulates a dish that gets a lot higher gain and allows us to send more data back to Earth.
Now, tell me a little bit about this propulsion system, because I'm thinking about the engines on a rocket when it takes off. That's not what's happening with MarCO.
No, so the fluid inside the propellant tank is essentially what you would find in a fire extinguisher. So if you've seen the movie WALL-E, there's this scene where WALL-E flies around space using a fire extinguisher and it propels him all the way around.
Right.
That is essentially what MarCO is doing. The thrusters are much tinier, but we actually nicknamed the spacecraft WALL-E and EVA because of that. So we have 8 total thrusters on the spacecraft, and we're using them for 2 things. One is to do what we call trajectory correction maneuvers, which are basically course corrections. So as MarCO flies, we can control its trajectory fairly precisely. And there are thrusters that allow us to change the orientation of the MarCO satellite while it's in space.
So basically, it's going to be kind of kicking out compressed air. Okay. Now, tell me about this radio. From what I understand, it's something new. It's built right here at JPL. Tell me a little bit more about that.
Yeah, so the group at JPL designed this antenna specifically to operate with the Deep Space Network, and MarCO is going to be the first mission to fly this technology. So we've done a lot of compatibility testing with the Deep Space Network, and so we've shown that it's configured well and it will work. We just now need to fly it.
Okay, and then third is the dish. This trifold.
This trifold antenna. Yeah, it's called a passive phased array. And so one of the reasons why it's such a cool technology is when you launch a CubeSat, or any satellite in general, volume is a hot commodity. And so in a CubeSat especially, because the whole satellite has to fit into a box, the more box-like all of your components are, the better. And so this antenna folds into a volume about this high when it folds down, but it opens up. It's fairly large, and it simulates a much larger dish that would otherwise have to be curved and would be much harder to actually stow in that volume. So it could enable a lot of really cool communications technologies in the future.
Tell me about what your role will be with the mission as they fly to Mars.
I will be operating one of the MarCO spacecraft, and for this mission, what that means is we'll be sitting on a console computer sending commands and receiving data from the spacecraft. So before every chance we get to talk to it, we get about 1 chance per day. We'll have a set list of commands and scripts that we want the satellite to execute. And so we'll upload those via the Deep Space Network, all remotely. And then as it's happening, we'll get that data back and see what the spacecraft is actually doing. And hopefully it'll be doing exactly what we told it to do.
Joining us now is Joel Steincross, the mechanical lead for MarCO. How you doing, Joel?
I'm doing great here, Chris.
You know, Annie did a great job talking about 3 technology innovations that you've implemented into MarCO. One of the things I'd like to focus in on for a couple minutes is the thermal protection system. You know, generally when we design spacecrafts, we send them out to places beyond low Earth orbit. You got to protect them from the cold, from the hotness of space. But when you get a size of MarCO, which is a pretty small satellite, and we were talking CubeSats, how do you protect that thermally?
You're absolutely correct. The harshness of space's thermal environment is a difficult challenge to overcome. I've heard it described as trying to pick a single outfit that'll simultaneously allow you to run a marathon in the Sahara while going snowshoeing in the Arctic. And the solution that we've put together for this is a bespoke suit of thermal blankets that MarCO wears that is the perfect balance of an outfit for its 6-month voyage all the way to Mars.
Yeah, because you're going to be traveling, I believe it's something like 158 million kilometers.
Yeah, it's a long journey, and our environment changes all the way. We're getting further and further from the sun every single day, and so you have to have a thermal system that will adapt and accept the heat when you're closer, but also the cold when you're further away.
All right, so the question is, if you're using technology that can protect the spacecraft for such a long journey for 6 months, how can we keep that coffee warm?
Absolutely, yeah. So we cover the outside of MarCO primarily in thermal blankets. So these are multi-layer blankets that allow MarCO to snuggle in into bed and not lose the majority of its heat. Being a CubeSat, we have a very precious amount of power that we're trying to keep. And if we are losing that, we have to add more power to our heaters. But that being said, MarCO can still get toasty sometimes. So we have a radiator, which is MarCO's way of sticking its foot out from underneath the covers in order to not get too warm on its flight.
Well, I tell you what, Joel, this is going to be exciting because this is the first time that we're going to have CubeSats leaving low Earth orbit and going to another planet. And I wish you all the best with you and your team. And we can't wait to see maybe some of the transmissions coming from MarCO, from InSight.
Thanks so much, Chris. We're really excited to see MarCO deploy from our dispensers and come to life and start our mission.
We've been talking about InSight, we've been talking about MarCO. So now let's turn our focus to the launch vehicle, the Atlas V. Standing at the pad right now, we have Tiffany Nail and Mick Waltman of the Launch Services Program. Tiffany?
That's right, Chris. We're here at Vandenberg Air Force Base, Slick 3, and the tower has rolled back. Mick?
Yeah, it's great to see this rocket behind us, isn't it? The MST started on time at 11:30, moving, got it into the park position right now, exposed the vehicle, and showing off all the beauty of this Atlas V.
The last time we were together, it was for the show for GoZest, where we had an Atlas V 501 roll out. What's the difference between the two?
Yeah, on the East Coast, we build the vehicle, assemble it, test it in the vertical integration facility, and then we roll it out to the pad. Here at Slick 3, what we do is build and test the vehicle inside the mobile service tower, and then we move the mobile service tower to the back of the pad and expose the vehicle, get ready for launch tonight. So just a little uniqueness between the East and West Coast to processing, but ULA has done a great job processing this vehicle, getting it ready for the InSight mission.
Now, why did LSP pick the Atlas V 401?
So yeah, the 401, great configuration, 4-meter fairing, 0 solids, single engine Centaur. LSP selected the 401 for the InSight mission due to spacecraft requirements and the mass of the spacecraft. Most of our Mars missions have launched off the East Coast, going easterly, which gives us a little extra boost with the Earth rotation added to the vehicle thrust, right, to get into that interplanetary trajectory we want to go. But this will be the first interplanetary mission from Vandenberg, and it's a historic site for the Atlas vehicle, a ULA LSP, and we're just looking forward to it. It's exciting.
Very exciting. I mean, even with the media here and everybody here to get a picture, it's just Over-the-top excitement, and we love that because, like you said, Mick, this is historical. This is historical for California residents, and they're just very excited about this mission.
So one of the things, again, we talk about the launch, right? We launched tonight. We'll be going southerly from Vandenberg. We'll go around Earth into a polar circular orbit, and when we get to the North Pole, we'll do that second Centaur burn, which will be a couple minutes long. That second Centaur burn will then loft InSight into its interplanetary trajectory there. That's what we're going to do earlier this morning.
Now, talking about the Centaur, we have a couple hitchhikers called CubeSats, MarCO A and B. What's LSP's role with those?
Yeah, we're excited about those. I mean, InSight is the primary mission, but MarCO A and B, part of the Alana initiative with LSP, right? And what it really cool is MarCO A and B will be the first interplanetary CubeSats heading out of Earth's orbit. And they're going to follow InSight to the red planet, and part of their job will be to radio communications and telemetry back as InSight descents into Mars. They'll be testing some other technologies and things like that, but it's really cool to see these little CubeSats on their way doing some really important science along with the primary mission of InSight.
Now, Mick, this is going to be our third launch once InSight launches, and we have 3 more. Can you summarize the 3 that we have after this?
After we launch InSight this evening or earlier this morning, we've got an ICON mission, which is going to be going on a Pegasus later the year, and then Parker Solar Probe, which will be launching on a ULA Delta IV out of Slick 37 at Cape Canaveral Air Force Station. And then to top our year off, it's our 20th years of program, 6 missions, 6 launch sites. It's exciting. We're going to top it off with our last Delta II right here at Vandenberg Air Force Station, ISAT-2 mission out of Slick 2.
Which is going to be exciting for a lot of people on our launch team. I mean.
Absolutely. It's a lot of folks have worked with Delta II. It's been a workhorse for NASA. But, you know, tonight we got the big beauty behind us, the Atlas 401, which is becoming our mighty rocket for a lot of NASA missions, including InSight today. We're really excited to get this one going. Again, first ever heading to Mars from Vandenberg with the ULA Atlas V rocket.
So now the launch team is on console as we speak. They're counting down to T0. Let's get this rocket off the ground. InSight's on its way to Mars along with MarCO.
6, 5, 4, 3, 2, 0. Liftoff of the Atlas V, launching the first interplanetary mission from the West Coast. And NASA's InSight, the first outer space robotic explorer to study the interior of Mars.
The InSight spacecraft is on its way to Mars.
And the MarCO CubeSats were successfully deployed, so it's all systems go for Mars.
Next stop, Elysium Planitia.
When we're there, we'll get some data, get some data, get some data, get some data.
You're crazy.
Continues to look good at this point in the mission.
You're watching NASA Edge.
An inside and outside look at all things NASA.